All right, thank you very much. So, how many of you remember approximately 2 years ago when I gave a talk about gravitational lensing for the 100th anniversary of general relativity? Oh, some of you. Even if you're just pretending, that makes me feel good. So you're already experts, so we can skip right to the technical stuff. Only joking. So the first two talks tonight, me and Brianna, who'll be following me, are both concerned with the same general question, which is how do we get the kinds of galaxies that we see around us today? Where did they come from? How did they form? And how did they evolve? And we use different techniques to study this question. I'm concerned with pushing it to the extremes, seeing the very, very first galaxies using space telescopes. And then after me, you'll hear more about how we can look at the detail of galaxies using ground-based telescopes, including ones here in Texas. So how do we see how galaxies formed and evolved? Now, luckily, physics has given us a really, really good tool to do this. I know, it's really upsetting. I feel like that too. Which is the finite speed of light. Because light travels at a finite speed, we see everything in space as it was sometime in the past, the amount of time it's taken light to get to us. When you watch the eclipse on Monday, you'll actually be seeing the sun as it was 8 minutes ago. The sun's pretty close, of course. If you look at stars, you're seeing them usually as they were a few years ago. If you look at galaxies, you're seeing them at least a few million years in the past. But we can push this even further and see things billions of years into the past. And by doing this at lots of different times, so seeing galaxies at different distances where the light has taken different amounts of time to reach us, we can piece together how, on average, galaxies formed and evolved. Of course, we can't watch one single galaxy evolve because it takes billions of years and we don't live that long. So by doing this, this is how we've pieced together the history of the universe. And we have a pretty good picture of it. If you think that we're just one little carbon-based life form on one little rock orbiting one little star in an uninteresting corner of one galaxy, and we've seen things back to almost the beginning of time. This is pretty cool. So this is our history of the universe. We know there was a Big Bang. The first very, very, very tiny fraction of a second, little bit of a mystery, physics kind of breaks down. But from then on, we think we have a fairly good handle on the big picture, at least, of what happened. We had this big hot soup of particles that formed into protons and electrons, which combined into atoms. And gradually, these atoms fell together under gravity and formed stars, which grouped together into galaxies. And these galaxies then formed spiral arms, and they collided and turned into these big ellipticals and the kinds of things we see around us today. So we've got the big picture, and now we want to dot those I's and cross those T's and figure out, when did this happen? When did these first stars turn on? And this is really difficult to do for two reasons. First of all, to see things at the beginning of time, you're looking really, really far away. The light has to have traveled for most of the age of the universe for us to see them. Second of all, because they're in the first stages of formation, they are intrinsically small. They're just starting to form. So they're very small and they're very far away, which makes them look smaller and fainter. So this is really, really hard. But we do it anyway, because why not? So the period of the universe that I'm most interested in is kind of around here. This is not on a nice linear scale, because if it was, most of it would be really boring, from my point of view. Brianna will disagree. So I'm interested in this period, like from when the first stars formed up until when star formation peaked. So we're talking about the first few billion years of the universe. And how can we tell that these galaxies are really, really far away? We can tell because almost all of the universe is hydrogen. This is still true, but it was especially true in the early universe when most things were just a single proton with an electron. So I'm sure you all remember from your high school physics what a hydrogen atom looks like. Got one proton, and then it has an electron, which it can't just sit anywhere around this proton. it has to exist in one of a few discrete energy shells, and it can jump between these shells, but it can't live in between them. We call these shells ends 1 through, I've labeled 3, but theoretically they go to infinity. And the electron is going to jump between these shells depending on how much energy it has. So let's put our electron here. It's on the n=2 shell. This means it's received some amount of energy and it's kind of excited. It's jumped up to a high energy level. It's going, yeah. And then at some point, gets a bit bored, needs a rest. And so it's going to drop back down to the first shell. And when it does that, it's emitting a very, very, very specific amount of energy that translates to light at a wavelength of 1216 angstroms. An angstrom is just a unit of distance. It's 10 to the minus 10 of a meter. This really specific energy is incredibly useful to us because this is a really, really common transition when you've got a bunch of hydrogen sitting around. So if we're looking at a galaxy, this is a random galaxy with a telescope. This is our Hubble Space Telescope down at the bottom. And we have a cloud of hydrogen sitting between us and this galaxy. What's going to happen to the light as it goes from that galaxy towards us? Well, the red and the green light here is totally fine. But there's some of this blue light that gets gobbled up by these hydrogen atoms because it's looking for that specific amount of energy, this 1216 angstrom wavelength of light, that's going to cause the electron to jump up back to the n=2 level. And eventually it does get bored again. It emits that photon, but it does it in a random direction, which means that our blue light here is bouncing around in all different directions, and the odds of it landing on the Hubble Space Telescope are very, very slim. So what we see when we look at this distant galaxy, lots of red light, lots of green light, no blue light. And this is really useful because as the universe expands, the exact position of that blue light gets shifted towards the red, what we call redshift. And so by looking at exactly where we see that break in the spectrum, we can tell approximately how far away a galaxy is. So this is what it looks like in practice. Whenever we observe galaxies, we look at it through a single filter at a specific wavelength. Here are some of the filters that we use on the Hubble Space Telescope. You don't need to know exactly what wavelengths they are, but we're starting from blue, going through to, this is kind of at the blue limit that your eyes can see. When you get to the F814W in the middle there, that's kind of at the reddest end that your eyes can see, and everything to the right of that is in the near infrared. So we take an image of our galaxy in each of those filters, and we might see something like this. So we see nothing at all in the bluest filters, and then we have this booming bright galaxy in the reddest ones, and I assure you, to me, that is a booming bright galaxy. And by looking at exactly where that galaxy drops out, in this case it's dropping out in that F814W filter, this tells us that this galaxy is seen about 1 billion years after the Big Bang. Now, if we look at this galaxy, this one we can only really see in the very reddest filter on the Hubble Space Telescope. This tells us this galaxy is probably being seen around 500 million years after the Big Bang. And this is where it gets really problematic, because if you're seeing a tiny little speck like that in only one of your images, is it real? Is a speck on the detector? Is it random noise? You don't really know. So it's really, really difficult to detect anything at that distance with the Hubble Space Telescope just because of the wavelength coverage. And we can't go any more distant than that because then they're going to drop out of our reddest filter as well and we won't see anything. We have another problem too, which is that galaxies aren't all uniform. You get very, very bright ones, which are extremely uncommon, and very faint ones, which are more common. This is what we call a luminosity function, which is just a fancy way of saying we count how many galaxies there are at different brightnesses. Because astronomers use really weird units, it goes from bright to faint. Faint is on the right-hand side. And you get very, very big galaxies like this, are way down here, not common at all, extremely rare. Little galaxies, like this Magellanic Cloud, are extremely common. So if you want to look at what a normal galaxy looks like, or where most of the energy in the universe is coming from, that's these really, really numerous, but individually very faint galaxies. but because they're faint, you can't see them. So most of what we know about galaxy evolution at early times is really talking about these bright galaxies, which we can see, but they're not really the most common. They're really the most extreme examples. And this is where gravitational lensing comes in. Gravitational lensing is the coolest thing ever, and it falls out of Einstein's theory of general relativity, which tells us that space is not an empty arena in which stuff in the universe happens. It's actually an active participant in the goings-on of the universe. So if you have empty space, imagine it's two-dimensional, it's easier. Things can move through it, it's flat, things go in a straight line. If you introduce mass, it distorts space, so it curves it, and now anything moving through that space is going to move in a curved line. Now, this is quite intuitive if you think about other matter moving through space. The reason the Earth stays in orbit around the Sun is that the Sun is distorting the space around it, causing this curve. The Earth thinks it's going in a straight line, but it's moving through curved space, so it keeps getting bent around and it stays in orbit. But this is also true of light. Light gets bent around when it moves through curved space. And we can actually use this effect. It happens even around a star. So the very first test of general relativity actually came from a total solar eclipse, when you can see how stars are positioned differently when the light is having to come past the sun. And people will be doing that measurement again next Monday. But stars are kind of small. I want to go big. So we use the most massive things in the universe, which are clusters of galaxies. So here we have the Hubble Space Telescope observing a distant galaxy. The light from that distant galaxy goes in all different directions, and a bit of it lands on the Hubble Space Telescope. You put a cluster in the middle, and that light gets bent around, and it's almost like a focusing lens, and it focuses that light towards the Hubble Space Telescope, whatever telescope you're using. I mostly use Hubble. So this has two effects. First of all, there are more arrows pointing towards our telescope than there were before. This means we get more light, so things look brighter, which is awesome. It's acting as a magnifying glass. The second thing you notice is those three arrows that have landed on the Hubble Space Telescope there are coming from different directions. So the apparent position of things changes when they're lensed. And you see multiple copies of the same galaxy, which is kind of cool. You can add those together and get even more signal. You can see them at different times because it takes different amounts of time for the light to travel each of those paths. It's incredibly cool. So here's an image of a simulation, rather, of what it looks like in real time, or in a real image. We're pretending the Whirlpool galaxy is really far away behind this cluster. Down at the bottom is where it really is, and you can trace it moving across here. And you can see it hits certain positions and it gets really, really stretched out into an enormous arc. So there are certain very small but very special positions behind this galaxy cluster where if a galaxy happens to live, I'm going to play that again because it's shiny. Ooh. It took me hours to make this, but it's so pretty. So our galaxy is moving across an unphysical speed. And you can see it kind of wobbles and then, ooh, massive arc. And we see those massive arcs in real life. It's really, really cool. They stretch out the galaxy so much that you can actually see details inside them. It's pretty amazing. But the downside is you're looking at very, very tiny, very faint galaxies behind a galaxy cluster. Galaxy clusters contain the biggest and brightest galaxies in the universe. So here's one from the Hubble Frontier Fields, which is the project I work on. It's one of the largest projects ever undertaken by the Hubble Space Telescope. It required 840 orbits of Hubble time. An orbit is around an hour and a half, for those of you who are doing trivia. And it took images of 6 galaxy clusters, including this one, MAX 0717, which is kind of a train wreck, because it's actually 2 clusters merging together. All the big orangey things you see are cluster galaxies, which I don't care about. I care about faint, tiny things that are behind them that we wouldn't ordinarily be able to see, but are magnified into view with lensing. And here's an example of one. Can you see it? This is the kind of thing I look at all day. It's really depressing. So no, you can't. The reason is that there's this bright thing in the corner here which is drowning out any signal. So most of what I spend my time doing is trying to model and subtract these foreground galaxies. So I take these really pretty pictures and make them horrifically ugly. But now you can see this little speck in the middle there, which is a very, very distant galaxy that we're seeing in the first billion years of the universe, that we can only see now thanks to gravitational lensing. So we had a paper on this out at the beginning of this year, which you may have seen. We had a press release on it. It was picked up by a bunch of news outlets. This technique enabled us to see galaxies that are 100 times fainter than anything you can see in the Hubble Ultra Deep Field. So these are the faintest galaxies ever seen in the early universe, which is really exciting. But lensing and the Hubble frontier fields in particular also produce results that no one expected. This is another Hubble frontier fields cluster called MAX 1149. Those of you near the front may notice that this bears a striking resemblance to my skirt. The thing that's really cool about this cluster is that there's one particular galaxy behind this cluster that's seen when the universe was about half its current age, that's imaged 3 times. Here's one, here's the second one, and here's the third. This is such a cool galaxy because it's magnified so much that you can actually see that it's a spiral, like our own Milky Way. But it existed when the universe was half its current age, which is really cool. This galaxy is so cool that it featured in 2 chapters of my PhD thesis. So there was already a lot of imaging of it. And then when we went back to observe it for the Hubble Frontier Fields program, something weird happened. This new spot of light appeared. So this zoom in here is one spiral arm, which is in one image of this triply imaged galaxy. And this one spiral arm happens to be multiply imaged itself because of this one foreground cluster galaxy. And this speck of light you see, you can probably easily make out 3 spots here. There's a 4th one that's a little harder to see down there. This is a supernova. It's an exploding star that just happened to go off at the time that this image was taken, or a little before it was taken. Now remember I said that it takes the light different amounts of time to reach each of the multiple images of a galaxy. So we could go to our lens model, where we've mapped where we think the mass is in the cluster, plot out how long we think it took the light to get to each of these images, and we can work out that this top image, we think the supernova probably appeared in around 1995. Too bad, we can't go back and see it until someone brings me a TARDIS. This one here was observed in 2014. And then there was this third image. And at the time this was discovered, astronomers were predicting that we would see this third image of the supernova somewhere between 2015 and 2020. Now, those of you who have really good memories of my talk 2 years ago will remember that at the time they were predicting end of 2015, first quarter of 2016, and I said, oh yeah, right, they're just saying that to get all the telescope time. Well, I was wrong. This is that third image of the galaxy. You can see no supernova. It was observed again in October 2015. This was about 2 weeks before my last talk. Nothing there. And then a few weeks later, just to spite me, here it is, December 11th. There's a really, really tiny faint. These don't look as pretty because they're much shallower images than the main Hubble Frontier Fields one. But there's a tiny speck there, which is that supernova reappearing. And so this is what my skirt is in honor of. It's reminding me that I made fun of something that was right. And if you pay attention, you'll see each of the images of the supernova light up with the correct time delays scaled. 4 milliseconds equals a day, I think. Each of the supernovae will go off in turn. So this is kind of the best we can do with the Hubble Space Telescope, which has massively expanded on the capabilities we had before when we were doing blank fields. So how do we do better than this? No one's going to give us more than 840 orbits on Hubble to do a better version of this. So I like to say that telescopes are like rain buckets. And if you're trying to collect rain in a bucket, for reasons, there are 2 ways you can collect more rain. You can leave your bucket out for a really long time. Well, that's what the Hubble Frontier Fields and the Ultra Deep Field and all these other deep things are. We can't really do better than that. Or you can get a bigger bucket. So this is our bigger bucket. This is the James Webb Space Telescope, which is due to launch from French Guiana in October 2018, so a little over a year from now. And this is what I'm going to Australia to work on. This is going to be extremely shiny for two main reasons. First of all, it's a bigger bucket. So here's a comparison of the mirror sizes. The mirror is what we really care about when we're talking about the size of telescopes. Spitzer over here is a teeny tiny little telescope, which is the best one previously that's observed in the same wavelength range that JWST is going to see. Hubble here is the best telescope we have at the moment. It's actually pretty small. And then James Webb is going to be 6.5 meters across, really is gold-plated, super shiny. And so this is going to let us see much, much fainter things that we can normally see. But it also does something else that's really cool. You remember this plot of a galaxy observed in different filters with the Hubble Space Telescope? Well, James Webb goes further into the infrared. So squish those up and we can add more onto the end. So this one here, F160W, was the last Hubble filter, and these extra 4 are from one of the cameras on the James Webb Space Telescope. So if we bring up that galaxy seen 500 million years after the Big Bang, the one we could only see in one filter with Hubble, now we can see it in 5 filters. So we're going to be much more sure that these things are really real. But we can also go even further than that, because look, we've got all that wavelength to play with. We can go 370 million years after the Big Bang. That would look something like this. We're still seeing it in 4 filters. We could maybe even get 270 million years after the Big Bang and still see the galaxy in multiple filters. Of course, here we're getting a bit dicey because galaxies that soon after the Big Bang we're expecting to be very, very faint, maybe not as bright as that one. But theoretically, if they exist and if they are that bright, we're going to see them with James Webb, which is super exciting. So in conclusion, the thing you should take away from this talk, Hubble is awesome. Hubble plus lensing, awesomer. JWST plus lensing is the awesomest. So before I go, I want to take one more opportunity to advertise 2 talks I have coming up before I get kicked out of the country. 2001: A Space Odyssey. We're screening the movie at the Alamo Drafthouse Mueller tomorrow night. If you really want to listen to me again, come to that. There are a few tickets in the front row left, I think. And then I'm squeezing in one more because there's a very special event coming up, which is the 30th anniversary of Star Trek: The Next Generation. The anniversary is in September, but I'm moving on the 1st of September, so we're squeezing it into August. Someone's Dropbox didn't update, so this is actually on Tuesday, August 29th. I was only told that today. We're going to screen Star Trek First Contact, and then I will rip the science to shreds because it's fun. So before I go, I hope you will indulge me for just one moment, because I want to tell you a story. 3 years ago, when Jeff and I were starting Astronomy on Tap, we initially thought it would be a really cool thing to do through the department, right? But we both worked for the Department of Astronomy at UT, and we were met with not indifference, not no, but hostility. Luckily, we were both kind of obnoxious, so we just went, well, screw you guys, we'll do it anyway. And we did it in our own time and on our own dime. It was thousands of dollars of our own money that we put in to make this happen with no real knowledge of whether it would work. So when I say thank you to you for coming to this, I want you to know that it's absolutely sincere, because I was only vindicated because you guys showed up, and you've continued to show up for 3 years, and that's really awesome. And the fact that you're still here a year after we handed over the reins gives me some faith that this is a thing that's going to continue. And if this is the only legacy I leave behind in Texas, then I'm pretty happy with that. Also, and thing number 2, like all stories, this one has a moral, which is that when you know you have a good idea, do not allow anyone else's lack of imagination to hold you back. Do it anyway. Thank you very much.
Thank you, MC High Z. I know that you'll have a legacy on me, so like, don't worry about it. It's just like, come on. We all love you. Let's go. Let's ask her some questions. I didn't say anything on Twitter, so right here.
Oh yeah, the fact that the universe expansion is accelerating, what kind of issues with gas growing and so it's constantly accelerating.
So the question was, the fact that the universe's expansion is accelerating, how does that affect our measurements? So if you try to take any of our measurements and turn them into physical quantities, it has a big effect because you have to assume how much the universe has expanded since the time the light left the galaxy. But this is why when we talk about distances to galaxies, we use redshift, which I would do in a public talk. But redshift is just the amount that the light has been shifted to the red, which we can then convert into a distance and a time, but the redshift measurement is absolute. And so if someone else updates the cosmological parameters, which I'm sure they will one day, we can change the distance, but the redshift is still real.
Right in front.
Question was, how do we tell the difference between images of galaxies and real galaxies? So do you mean whether or not they're lensed? Okay, so the way you do it by eye is galaxies in clusters tend to be red. And so if you see something that's blue, and especially if it's kind of stretched into a weird shape, then it's probably lensed. But the main way you can do it is you know how far away the cluster is, you measure the redshift. We then take the redshift of a galaxy we're looking at, and if it's behind the cluster, it has to be lensed.
And this little guy up in front.
Ooh, the question is how many light years away are the first galaxies? So you have no idea how difficult a question that is. Because as we've discussed, it depends on your cosmology. It depends, do you mean how far away, how far has the light traveled? In which case we're talking like 13 billion years, so that'll be 13 billion light years. But that's not really true because the universe has expanded in that intervening time, so it's actually more between 40 and 50 light years, 50 billion years rather. It depends what you mean. All the space at the beginning of time was crammed into one tiny singularity that has expanded out. So that light from the beginning of time is everywhere. We still see it actually not from the beginning of time because light couldn't get out, but from the soonest that light could get out from all the dense material. This is what we now see as the cosmic microwave background, which is like noise that we see all the way across the sky. So when we talk about seeing back in time, it's not that we're seeing, oh, that's the point where the Big Bang happened. It's we're looking at things so far away. We were once all in the same spot, but they're now so far away that we see them as they were in that very early universe. If that makes sense.
It's deep. In the middle here.
So when you're looking at galaxies being lensed, do you have a good understanding of exactly where that galaxy is, or would that require a deeper understanding of the massive objects that are lensed?
Okay, so the question is, when we're looking at a lensed galaxy, do we have a good idea of where it is, or does it require a knowledge of the mass in the foreground? The answer is yes to both. I skipped over the part where we have to model where all the mass is in the foreground cluster. But what this image here is showing, the background is a galaxy cluster. Overlaid in cyan is where the mass is, which someone has taken a lot of time to model. That someone was not me. And then in magenta, this is the magnification. So this is showing that the really high magnifications, where you can actually see the magenta, are in really, really tiny specific regions, kind of in a line around the edge. And this is all modeled based on where we think the mass is. most of the mass is dark matter. So it's difficult because we can't see dark matter, but it's easy because dark matter is a lot more well-behaved than normal matter. It tends to just hang around in nice, big spheroidal halos instead of collapsing into little spinny disks. So we look at these galaxy clusters and say, okay, each galaxy in that cluster sits in a dark matter halo, and then we run a bunch of simulations in computers to figure out how massive would that dark matter halo have to be to recreate the kind of shapes we see in the distorted images on the sky. And we build up a model which, based on the recurrence of the supernova, turns out to actually be quite good.
That's why Rachel does the coolest stuff in the UT astronomy department. Okay, let's give her a hand. Thank you, Rachel.